buoyant force, alright, which you also call it as upthrust, an iceberg. So you have seen icebergs either in movies or maybe in real. Whenever any object is moving through the air or any fluid for that matter, it experiences a frictional force due to that fluid, assuming downward direction to be positive. So if I am drawing the graphs assuming downward direction as positive, so initially when you jump off the aeroplane, like any skydiver for that matter, it's going to experience. Hello students, welcome back to another exciting class on forces. We have already discussed a lot about forces, like what are the various types of forces. We have talked about impulse and momentum also. This is a big unit. There is a lot to learn and we are continuing with some more types of forces in this particular class. Alright, so without wasting any time, I think let's get started. Alright, so put down the heading buoyant force, alright, which you also call it as upthrust. So if you remember, we have talked about just the brief of the various types of forces and this is in continuation with that. So the force that we are going to talk about today is the buoyant force or the upthrust. So put down that heading. Alright, so this gentleman is Archimedes. He has a say in this particular force. Let's find out what. So first let me read it out to you. All fluids in the presence of gravity exert an upward force known as the buoyant force on any object immersed in them. So now you understand what this is about. Imagine you are swimming and do you experience an upward force? Think about it. Of course, yes, that is why you are able to easily swim. Or think about a wooden block that you have thrown in water. Does it sink? Of course not. It floats at the top of the liquid surface. What does that mean? That block is in equilibrium. So is the weight not acting? Is the gravity not acting? Of course it is. But then someone is cancelling that force and that force is upthrust. So what is upthrust? It is a force experienced by any object when immersed in a fluid. So when I say fluid, it means both liquids and gases. So upthrust is provided by both liquids and gases, but you don't feel it that much in gases. It is very evident in case of liquids like water. Alright, that is why big ships are able to float on water. That's because of the upthrust. What causes this upthrust? Let's find out. Alright, so the thing I have shown here is for simplicity a cylinder, because this is something that we all can easily relate. Now imagine this is a cylinder immersed in water or any other liquid. Now we need to understand first that there is a pressure at different levels in a liquid, which is given by, let's say, pressure here is P1 and pressure here is P2. Okay, so you might be knowing the basics of pressure. I am assuming that. And now let's say if this is P2 and this is P1. So as we go down in a liquid, the pressure increases and the difference in this pressure, I will quickly write that for you. P2 minus P1 is going to be rho GH, where H is the difference in the levels, alright, and rho is the density of the fluid. So this is the first background thing that you need to know, that pressure at lower levels is always more than the pressure at higher levels. So this pressure difference causes a net force. This is what Archimedes found out, that whenever you immerse something in a liquid, it does experience an upward force causing a loss in weight. That is how he was able to test the purity of things. For example, the crown of the king of Sicily, he was able to do that. So he was a great mathematician. At that point in time, he was able to figure out that whenever anything is immersed in a liquid or a gas, it experiences an upward force, and he gave a principle for that as well. We will discuss that. Alright, so let's come back to this. One thing again, pressure at lower level is more than pressure at higher level. So P2 is greater than P1 and this pressure applies a pushing force, let's say F2, while this pressure applies a pushing force downward, that is F1. Now since P2 is greater than P1, F2 will be greater than F1, alright. So what is this difference? F2 minus F1, this is the net force applied by the fluid or the liquid on the object immersed in it. Alright, so what is this? So you would say this is pressure times area, but of course because pressure is force upon area, so force is going to be pressure times area. Now what is this? P1 times A. So what is this difference? P2 minus P1 times A. This is the net upward force, which we may call as the upthrust, or we may call it as the buoyant force. Alright, what is this equal to? So you would say rho GH is the difference in pressure times area. Now think about this term. I will wait. Think about this term. Rho GHA. Rho is the density of the liquid, H is the height, and A is the area, alright, the area of the cylinder, the base, the circular area. Now imagine, what can you write for H times A? Can we say the volume of the cylinder? Volume of the cylinder. What is that? You would say it is A, let's say it's V, that is equals to A times H. So can we write this A times H as V? Of course we can. So this terms becomes rho Vg, where rho again is the density of the fluid, V is the volume, and G is the gravity. So can we write this rho times V as mass? Density into volume is mass, of course you know that. So this becomes weight of liquid displaced. Alright, so this is what triggered Archimedes, that when he sat in the bathtub, some water spilled out of the bathtub, and that gave him an idea that something has to do here with the amount of water anything spills out or displaces. That is related with the upward force. Now think about this. What is this? This is the weight of liquid displaced. So any object when immersed in the liquid will displace some liquid, isn't it? And the weight of the liquid displaced is equal to the buoyant force. That is what we have proved. This force minus this force is the net force, and that is equal to the weight of liquid displaced. So what are the three terms that govern this force? Rho, that is the density of the fluid. V, that is the volume displaced. G, that is the gravitational field strength or gravity. So keep this in mind because we will need this to do the questions further. Alright, so now let me read out the Archimedes principle for you. Archimedes principle states that the upward force that is exerted on a body immersed in a fluid, whether fully or partially, is equal to the weight of the fluid that the body displaces. So what decides the buoyant force or the upthrust? The weight of the liquid displaced. So more volume you displace, more upward force you will get. That is how heavy ships of iron are able to float. They displace large amount of volume. They have a large amount of hollow volume. So that displaces a lot of water, and that creates a huge amount of upward force that is able to balance the downward weight of the ship. That you might be having an idea, but still, just to quickly revise that you need to know all this before we start with the questions. So I hope now the buoyant force is clear to you, and you can write down the important stuff, and then we move forward. Alright, so buoyant force, this is now a question including that concept, an iceberg. So you have seen icebergs either in movies or maybe in real. So what is an iceberg? Basically it is huge, you can say mountains of ice floating in water. Now why does ice float on water? So in general you would say anything that has lesser density than water will float on water. Anything that has more density than water will sink. So like an iron ball will sink if it is entirely solid because it has more density than water. But ice still floats. So that is quite surprising that ice, in spite of made up of same molecules as water, like liquid form of water, still is able to float. So solid is floating means solid has lesser density and the liquid version has more density. Normally you would expect solid of anything to be more compact and hence having more density. But here solid, that is ice, is lighter. As you can see, the density of ice is 900 while that of sea water or ocean water is 1050 kilogram per meter cube. Alright, now what is the question? What percentage of the iceberg is above the surface of water? Alright, let's do this. It is floating. What does that mean? The downward force that is due to the weight, isn't it? The downward force that is due to the weight is equal to the upward buoyant force. Only then it can float, of course. Alright, so let's write that. Since it is in equilibrium, buoyant force, I am writing it as FB. You can call it as upthrust. Okay, so there is thrust even in air, but it's something that we cannot easily feel because air is very lighter than water. But let's say a helium balloon, there you see it rising. That's because its weight is less and the buoyant force is more, and that is why anything that is made up of material which is lighter than air can even start rising in air or float in air. Alright, let's come back to this. So let's imagine the total volume. So let's make this total volume is V. Alright, so total volume, that is the volume above as well as below the surface, right? While the submerged volume, let's call it as V1. Alright, so this is what we know now. So buoyant force, this buoyant force will be equal to density of water times V1 times G. So now are you able to understand what three parameters decide the buoyant force? Density of the fluid, that is water in this case, volume that is displaced, that is inside the water, times gravity. And what is the weight? So you would write rho of ice times volume times G. Now can you imagine? G cancelled out, so the buoyant force and the weight both depend on the same gravity. So this factor gets cancelled out, and what we are getting is that V1 is rho of ice over rho of water times V. So let's do this calculation very quickly because the data is clearly given. This is going to be 900 divided by 1050 times the volume, that is, let's say V, we don't know what it is. So 900 divided by 1050 is giving me 85.7. So I will write it as 86%. Alright, so I'm already converting that to percentage. If this is the fraction, multiplied by 100 and you will get the percentage. So 86% of V is inside the water. So how much is outside then? Obviously the remaining part. So we can call this 86% of V. So this would be 14% of V. Alright, if you see any iceberg, if you see an ice cube floating in a glass, the part that you can see above is only 14% of it and the 86% remaining is inside water. So if you see an iceberg that is huge, so don't get amused, but it is way bigger inside the water. It's only 14%, so it's only the tip of the iceberg in that sense that you're able to see. Remaining 86% is inside water, so that is to be taken into account. You cannot just rely on the vision and think of, you know, navigating through the icebergs, because the amount of ice that you have inside the water is way huger as compared to the part that is outside. So that is what the question was all about. What percentage of the iceberg is above the surface of water? And I hope you're able to understand that is going to be 14%, which is above the water. Let's do this. This question now includes two different liquids. So now imagine water is heavier than kerosene oil. That is why water settles at the bottom and kerosene oil is above water. Now the term here is specific gravity. That is always relative density, like density with respect to something. That is the ratio. So, and specifically we talk in context of water because that is the most common liquid we can think of. So if they are saying that specific gravity of oil is 0.8, so if we take density of water, distilled water, that let's say this is 1000 kg per meter cube, then density of oil here, that is kerosene oil, will be 0.8 times of 1000. So that is going to be 800 kg per meter cube, while density of ice is 0.9, that is 900 kg per meter cube. So I've collected the data for me. I know the densities now. What are they asking? They are asking the ratio of ice immersed in water and kerosene oil. So let's call this volume as V1 and let's call this volume is V2. So V1 is the volume of ice cube inside water and V2 is the volume outside water but in the kerosene oil. So can you imagine why this ice cube first sinks? Because ice is denser as compared to kerosene oil. So it sinks, but it does not go into the water. Why? Because water is heavier than ice. That is why it adjusts itself at the interface, some part of it in water and some part of it in the kerosene oil. Alright, so let's quickly wind this up. Since this is an equilibrium, we can write FB1 plus FB2 equals to the weight. So equilibrium, downward force is equals to upward force. What is the downward force? Weight. What is the upward force? Buoyant force due to both the liquids, right? So that is why I'm writing it in two parts. Now let's do it. So the first part is for water. So it is going to be rho water into V1 into G. For the kerosene oil, it is going to be rho oil into V2 into G. And what about the weight? What about the weight? The weight is going to be due to the whole volume. So can we write rho ice into V1 plus V2 into G? That is the equation I have made. You can give it a try. Rho water, this is the buoyant force due to the water, this is the buoyant force due to the kerosene oil, and this is the overall weight. Put the values 800, 900 and 1000, you are going to get V1 equals to V2. What does that mean? That means this ice is 50% inside water and 50%, the data is like that, it adjusts like that and the value turns out to be equal. V1 is equal to V2. That is not compulsory, only for this data it is happening. Alright, so that is about buoyant force. Now you have an idea how to write another kind of force and how to include another type of force in your free body diagram. So I hope you remember in the last class in the last few classes we have been talking about free body diagrams now, and you should be more confident with that. Alright, copy down the important stuff, then we move forward. Alright, now let's talk about the next type of force, that is the viscous drag or the viscous force. That you do understand that whenever any object is moving through the air or any fluid for that matter, it experiences a frictional force due to that fluid, right? So that is what we call as the viscous drag. So if you remember in kinematics, we were always doing questions of motion, but we were always assuming that there is no air resistance, because if air resistance comes into picture, there is another force that emerges and that is the viscous force. Alright, but it may be more prominent in case of liquids. So for example, if you drop a spherical ball and in air, it will quickly fall. But imagine what will happen when it is dropped on the surface of water and it enters into water. The viscous drag will be way too much and you will only see it moving slowly. So the viscous drag again depends on the type of fluid, isn't it? And we are today in this video majorly talking about viscous drag due to liquids, and then in the end we will also take into account the air resistance. Alright, so this is something I have here for you which we were discussing, that let's say there is a spherical object. The first force that acts on it is going to be the weight of the object, and that is going to be mass times gravity, and mass can be written as density of the solid into volume and multiplied by G. Just now we have learned the buoyant force acting on it will be density of the liquid or the gas or the air, whatever it is, times volume times G. So these two forces are there. Volume, this is uppercase V. This is for volume. Now let's say this is a spherical object. See, now what happens is that different objects have different shapes, and that makes this drag force very complex because it is area dependent, it is shape dependent. So we cannot deal with all the shapes right now in this class. So we are only discussing the case of spherical shape. But one thing is certain, that if you imagine you drop two things, whichever has more surface area will have a tendency to experience more drag force. And you can imagine why. Because this drag force is created by the collision of the object with the particles of the fluid. So if there is more area, then it comes in contact with more particles, hence applying more drag force. Secondly, which is something very new for us, it is also dependent on the velocity. Imagine something which is falling faster or moving faster will collide with more particles during some period of time. So again, more collision will create more drag force. So one thing that is to be kept in mind, which is very new now, that this viscous drag, let's call it Fv, is given by 6 pi eta Rv. So what are these terms? Let's one by one discuss. First, v is the velocity. So more the velocity, more is the drag force. More the speed, more is the drag force. R is the radius. Alright. So obviously more radius means a bigger body, and bigger body will always have more drag force. This is what this Sir George Stokes observed, this English scientist. He observed this, and this is therefore called the Stokes law. Alright. So this eta, so just like you had friction in solids, so it was very different in many contexts. For example, solids friction does not depend on the area. Solid friction does not depend on the velocity. Here, the friction in fluids, it depends on both the velocity as well as the area, you can say that. But this, the one thing that solid friction was depending on was the type of surface, isn't it? Type of interface. Here also, this is called the coefficient, as we called it coefficient of friction. Here we call it as coefficient of viscosity. So it depends on the type of fluid, as I was just discussing. Air will have lesser viscous force, while liquids will have more viscous force. What should be the unit though? It is not unitless. It has a unit. Think about this. This is Newton, this is meter, and this is meter per second. So the unit of this becomes Newton second per meter square. If you remember, Newton per meter square is pressure, which was measured in Pascal. So you can also write this as Pascal second. So it depends. You can use both of them. Alright. Now let's come back to this, and let's come back to the part where we are observing that it is dependent on velocity. Now imagine you drop something, what is going to happen? So it is going to accelerate due to gravity, but then the thrust force will also be there. In liquids, it's going to be quite prominent, and the net force will be this minus this, but still it is accelerating downward because the weight is more than the buoyant force. So we are imagining it to be like a steel ball where the weight is way larger as compared to the buoyant force. Now imagine when this is sinking, when this is sinking downwards in the liquid, there is another force that starts emerging, and that is the force of viscous drag, right? But this force is not constant. These two are constant. They do not change during the course of motion, but this force keeps on increasing. Now imagine if you draw acceleration versus time. Let's say if you draw acceleration versus time, then what would it be like? So you would say acceleration versus time should be like this. Now imagine why it should be like this, acceleration time, because this is constant, this is constant, this is increasing. So the force, this force, which is the opposing force, is continuously increasing, making this net force, overall net force, decrease. Again, this force is constant, obviously, while it is moving. This force is again constant, but this force is going to increase because it is accelerating. So because this force is increasing, these two combined are increasing, and the net force, that is this minus these two combined, is decreasing. So the net force is decreasing, and therefore the acceleration is also going to decrease. So imagine how would we have velocity versus time then? let's draw the velocity versus time. Alright, so let's think about it. Now what will be velocity versus time? I'm not saying velocity is decreasing, velocity is still increasing, but the acceleration is decreasing, so the gradient should decrease. So what should it be like? So you would say that velocity is increasing, but the gradient is decreasing. So the graph should be like this, and ultimately this force plus this force become equal to this force, and we would say at one point the net force will become 0 and acceleration will become 0, and after that you cannot imagine the velocity to further increase, and we would say that a terminal velocity is achieved. So that is what it is associated with. Terminal velocity is associated with Stokes' law only, where we are discussing that the net force is decreasing, the acceleration is decreasing, and therefore velocity after a point becomes constant as acceleration becomes 0. Alright, so that is what happens to any, let's say, asteroid. If it is entering into the Earth's atmosphere, after a point its velocity cannot increase due to gravity. Why? Because the viscous drag starts becoming so dominant that this force plus this force become equal to this force. So can we write it here? When terminal velocity is achieved, when terminal velocity is achieved, so what point or attained? So what point are we talking about? We are talking about this point. Once terminal velocity is attained, the net force becomes 0, or we can say that the viscous drag plus the buoyant force become equal to the weight of the object. Now what is the viscous drag? So you would say 6 pi, we pronounce this as eta rv, and let's call this as vt, and the buoyant force is going to be density of liquid times volume times g, and that is equal to the weight, that is density of solid times. So v is volume here, while v is velocity here. Keep that in mind. So this is lowercase v, this is uppercase v. Now what is the value of v terminal therefore? So this is going to be rho s minus rho l into vg divided by 6 pi eta r, isn't it? That is the terminal velocity. Alright, this terminal velocity you can rewrite as you know that volume of a sphere is 4 by 3 pi r cube. So use that expression, and let me change the color here, and the value of terminal velocity will then look like 2 by 9 eta, alright, r square sigma, or we can write rho solid minus rho liquid into g. So this is another way of writing the terminal velocity. So that clearly explains that bigger spheres will drop faster and smaller spheres will drop slower. In case of a liquid like this, the terminal velocity is directly proportional to the square of the radius. So if they are made up of same material, then the bigger sphere will move with more terminal speed, and smaller spheres will move with lower terminal speed. Keep this in mind, it is proportional to the square of the radius. So again think about it, what we have discussed. We have started talking about another category of force which is majorly associated with fluids, as was buoyant force, but buoyant force was majorly something that was related with any object that is immersed in a liquid or a gas. But here this is a force only associated with objects moving through the medium, right? So if an object is at rest, whether it is in, let's say, a rock inside water, that won't experience any viscous drag. Viscous drag is going to be there only if velocity is there, and the highlight is that it depends on the velocity. That means more velocity will have more viscous drag. All right, copy this down. This is very important, this behavior of acceleration versus time, and I'm assuming that you know that velocity versus time, the gradient is defined by the acceleration, and therefore acceleration is reducing. So I'm not saying velocity is reducing, velocity is increasing, but the gradient is decreasing, isn't it? That is why it increases initially at a higher pace and then it decreases and ultimately it becomes constant. Copy this down. We take some questions on this. All right, next one very quickly. A solid metal ball is falling in a long liquid column and has attained a terminal velocity of 4 meters per second. What is the viscosity of the liquid if the radius of the metal ball is 5 centimeter and its density is 8050 kilogram per meter cube? Alright, so just now we have discussed that terminal velocity was given by 2 by 9 eta r square rho solid minus rho liquid into g. All the data is given to us. All we have to find out is eta. So eta becomes 2r square over 9 times of V terminal times gravity times rho solid minus rho liquid. So let's do this calculation very quickly. So the radius is 5 centimeter. So square that, it becomes 25 centimeter to meter becomes 10 to the power minus 4. I hope you know all this. Now let's multiply it by the gravity value, which is given to be 10. Divided by 9 times of V terminal, which is given to be 4 meter per second, and rho solid minus rho liquid is going to be 8050 minus 1500 minus 1000, so that's going to be 7050. Let's do this calculation very quickly. So this is 2 times 25 times 10 times 7050 divided by 36. So what I am getting is 7, and now let's divide it by 10,000. All right, so what I am getting is 9.8. all right, 9.79, and the unit was Newton second per meter square. All right, so this is what I have done to calculate the terminal velocity. No, the terminal velocity was instead given, and to calculate the coefficient of viscosity, we use the formula for terminal velocity. All right, but I hope you remember how did we derive this. This expression will be useful if we are talking in terms of volume, and this expression will be useful when we are talking in terms of radius. All right, copy this down. I hope you try the numerical first and then you see the solution. So it's always a good habit. Pause the video right at the moment when you see the question. Try it and then see the solution. Don't try to see the solution at first. All right, so the next now, two balls of radius r and 2r made from same type of steel fall through a liquid that exerts a viscous drag force on the balls. The smaller ball reaches the terminal speed v. What is the terminal speed of the larger ball? So all we have to do is, just now we have discussed V terminal is proportional to the radius square. So V terminal 1 over V terminal 2 is going to be radius 1 square over radius 2 square, because all the other terms are kept constant. So if the radius is doubled, then what do you expect the terminal velocity to be? So let's say we are calling it as Vt2. Vt1 is given as V. First ball the radius is r, second ball the radius is 2r. Clearly V terminal 2 turns out to be V, so I don't see any problem whatsoever here. Again, these are very simple questions that I'm taking right now because you've just learned the concept. Now you will revise and we will start off with the previous year questions. There is, there you will ultimately apply your entire knowledge that you have gained through the classes. But don't break the chronology. Do watch the videos in a particular sequence that we are uploading. All right, the terminal speed of a sphere of gold is 0.2. Then the terminal speed of sphere of silver of the same size. So now the comparison is for two different densities. Here the comparison was for two different sizes. All right, so now what are we going to write? Vt1 over Vt2 is equals to rho solid 1 minus rho liquid over rho solid 2 minus rho liquid. Why so? Because all the other terms cancel out. Only the term that now we are left with is this one, and you can imagine why, because this is the expression. All the other terms will cancel out, and the only term that is different here is the density of the two balls. All right, so this is going to be, this is 19,500 and this one is like 10,500. So all right, let's put the values. While the liquid density is 1,500 500. All right, this is 1.5 times 10 raised to the power 3 kg meter cube. All right, 10 to the power 3 is also there. It is a misprint. All right, so what is this value now? 19.5 times 10 raised to the power 3 minus 1.5 times 10 raised to the power 3 over the sphere of silver that has the density of 10.5 times 10 raised to the power 3 minus 1.5 times 10 raised to the power 3. All right, so what is this value then? 19.5 minus 1.5, that is 18, and this is going to be 9. So this value turns out to be 2. All right, I hope you have done this calculation yourself now. So the terminal speed of gold is 0.2 and they are asking the terminal speed of silver sphere. So this is 0.2. So let me put the value here. Vt1 over Vt2 is 2 and this is 0.2. So Vt2 turns out to be 0.1. Is it? Easy. I think you should be able to do it. So the answer should be option A. So just to give you a feel that these sort of questions you might get. So 2 new forces we have introduced. Now we will talk about movement of liquids through air, and that is where air resistance comes into picture and how their velocity and acceleration changes. Let's quickly figure that out and finish off today's class. Copy this down, then we move forward. Alright, so now let's quickly wind this up. So the first thing, object falls under gravity. You already know they keep on accelerating due to gravity at a rate of 9.8 meter per second square. That is why the distance is continuously increasing as the velocity is increasing and it is accelerating. So let me read it out to you. The falling object accelerates as time goes by. For an object to accelerate, there must be force acting on it. In this case, it is the force of gravity that is pulling the ball downward. The gravitational force acting on an object is called the weight. All this we know. The earth pulls with a force of 9.8 Newton on each kilogram. So object of mass 1 kg has a force of 9.8 Newton. Let's draw the acceleration versus time graph, assuming downward direction to be positive. So if I am drawing the graphs assuming downward direction as positive, then the acceleration versus time graph would be a straight line whose value is going to be 9.8 meter per second square. So we are discussing without air resistance. All right, so we do not need to worry. The only force that is acting on the object is the weight, and that is why the acceleration is constant. Now velocity versus time, so it has to be a straight line, and the slope of this graph, let's say tan theta, is going to be 9.8 meter per second square. Again repeating, if you take upward as positive, then these graphs will be on below the x-axis, right? So keep that in mind. All right, now the displacement versus time. So displacement is continuously increasing, but the velocity is also increasing, so the gradient has to increase. So the graph should look somewhat like this: lower gradient, then higher gradient, then even higher gradient. Why? Because the gradient of this is given by the velocity, which is continuously increasing. So this time it won't be a straight line, it will be an increasing slope curve, right? So I hope you understand this. There's not much to do here, we have already talked about this. Now try to draw them. So with air resistance, so you would say we have just talked about it, the acceleration continuously reduces and ultimately it starts off from 9.8 though, but ultimately it becomes 0, isn't it? So when you jump off, let's say an aeroplane for skydiving or something like that, ultimately your acceleration will become 0 and your velocity will stop increasing thanks to the viscous drag. So what is the speed going to be like? So speed is increasing, but the gradient is decreasing, and at a point we achieve a terminal velocity when the acceleration becomes 0. What about the displacement time or the distance time? It is continuously increasing, but the slope of this is velocity, which is also increasing. So the distance versus time graph is going to be like this. Continuously distance is increasing, but the slope is also increasing because slope of this is given by the speed or the velocity. So I hope your answers match with mine, because now the terminal velocity concept is there because of the viscous drag. So it slightly differs from what we have done here, where the velocity was constantly increasing. Now velocity is increasing at a higher rate initially, and then it becomes lower and lower to become zero in the end. All right. So the last thing is, how does a skydiver, experience the drag force and everything? Let's have a quick chat about that as well. So initially, when you jump off the aeroplane, like any skydiver for that matter, it's going to experience a force of gravity and the air resistance and the buoyant force. So the buoyant force in case of air is almost negligible. We are not taking that into account. So the only force that is acting is the weight in the downward force, in the downward direction, and the viscous drag in the upward direction. So what happens here is, this remains constant, but this keeps on changing, right? This keeps on changing with speed. All right. So initially the drag force is almost negligible, and that is why you see the speed to increase at a constant rate of 9.8 meter per second square. But then here, let's say here, you see the drag force coming into picture. So let's say O2A, you can say that drag force is almost negligible and the object is accelerating, or the person is accelerating at 9.8 meter per second square, isn't it? But then the drag force starts coming into picture and the velocity starts reducing. So here we can say air resistance comes into picture, isn't it? Comes into picture, due to which the velocity starts increasing but at a lower gradient. This is where the terminal velocity is achieved, isn't it? And then for a while the skydiver is moving with that constant terminal speed, but he or she has not opened the parachute as yet. This point, let's say B terminal velocity is achieved. This point is when the parachute is opened. All right. And as the parachute is open, huge amount of surface area comes into play and the viscous drag becomes even more than the weight. And we can say the object starts decelerating, the person starts decelerating, because in this zone viscous drag becomes more than the weight, and that is why the velocity continuously reduces till again a terminal velocity is achieved. All right, again a terminal velocity is. Why does this happen? Because ultimately when the velocity is reducing, this force is becoming weaker and weaker and weaker, and then it balances off the weight again, and this is when the terminal velocity is achieved again. Terminal velocity but of lower value, which is manageable, so that when the person strikes the ground, he or she is able to take that much of an impulse. So that is how parachute ultimately lower down your terminal velocity and you strike the ground with a velocity which is manageable, and then you come in contact with the ground and then you finally stop. So that is the journey of a skydiver, and you now understand how drag force operates. It depends on the area and the velocity. So I hope you were able to relate with this. So this was my attempt to introduce the concept of two new forces today. One is the drag force and the other was the buoyant force. All right, so we'll keep coming with such videos, and you keep practicing, so that when we start with the previous year questions, you are able to do them yourself. And even if you don't, then with more questions we do here for you, you will be able to ultimately figure it out. All right, so that's all for this particular video. Happy learning. See you next time. Bye bye. If you enjoyed this video, please don't forget to like, share and subscribe to our channel.